Hello, this is Electrical Circuits tutorial series, part number 7. We'll be talking about combination circuits and combination rules. Now, for a combination circuit to be a combination circuit, it is a combination of series and parallel circuits combined into one circuit. And we'll use the method we've been using to tell whether it's series or parallel by tracing the circuit to tell which parts are what. We'll talk about the node rule here in a little bit. And what a node is, it's simply a junction point where two or more wires come together. And for the series circuit, we'll use the series circuit rules. For the parallel circuit, we'll use the parallel circuit rules. And when we start to find the expected values, we'll first have to simplify the parallel part into the equivalent of a series circuit. Now and then we'll redraw the circuit. It's not as difficult as it sounds. You've already been doing that in the parallel circuit. Whether you're using the resistors of equal value method, the product over sum method, or the reciprocal formula method, that is what you're doing. Now, the node rule simply means current in equals current out. So what that's saying is at the node where the current enters the parallel portion of the combination circuit, that current has to equal the current leaving the node exiting the parallel circuit. The only difference is that current will be split up by two or more branches in that parallel circuit. Now here's a combination circuit. One thing we got to keep in mind, a lot of times your series portion of the circuit is going to be outside of the parallel circuit, but we really have to look for a series string embedded into a parallel branch, which we do have in this circuit. So to be able to tell that this is a combination circuit, and also to determine what is a series circuit and the parallel portion of the circuit, we have to trace it like we've done in the rest. So I'm going to go with the arrows in the flow of our electron flow theory, and we have one path. We pass through R sub 1, our first load, and we still only have one path. So that has to be a series circuit. Now we get here to point A, you see that dot. That dot means that that's a node. We have two or more wires coming together. And as you see, we've got three right here. We have another one down here at B where it's exiting the parallel. Now we have two or more paths. We can go this way or we can go this way. If we go this way, we go through a one load branch. And you see right here, it tells us we have 200 milliamps on this branch right here, or 0.2 amps. If we go straight down from the node at point A, you see that we have two loads inside here, but only one path for the current to flow. So we have a series string embedded into a parallel branch right here. And then when we come out node B, we see we have 600 milliamps right here, which is a 0.6. Well, once we're out of node B, we only have one path, so we can really say series, and we can move this 0.6 or the 600 milliamps up here to R1 and say that R1 has 600 milliamps as well as the total circuit current. Now we're going to talk about the node rule first. Remember I said the current entering the node here at A has to equal the current exiting the node at B. So we have 600 milliamps total current, and here we show this branch has 200 milliamps. So to be able to tell what the current is going to be through R2 and R3, since they are a series string inside that branch, we simply take the 600 milliamps and subtract the 200 milliamps, giving us 400 milliamps or a 0.4 amps for that branch. So both R2 and R3, because they are a series string, will have that same 400 milliamps running through them. Now that we've discussed the node rule, we'll go on to the voltages. Now, here we see that we have 30 volts at R3, we have 40 volts at R4, and we have 100 volts total over here. Well, we know since there's only one load on this branch here with R4 at 40 volts, that has to be our parallel circuit rule, because the parallel circuit rule states that the voltage is constant across all branches. So we can take the 100 volts total volts and subtract our 40 volts, giving us 60 volts up here as a voltage drop for R sub 1. Now then, using that same, knowing that our parallel circuit is at 40 volts, and this series string inside this other branch has 30 volts on R3, then we can take the 40 and subtract from R4 and subtract the 30 volt drop on R3, and that would tell us we had a 10 volt drop on R2. Now we can simply also go up here and tell our resistances. The resistance of R sub 1, we know we have a 60 volt drop now, and then we have this 600 milliamps down here for our total current. So 60 divided by 0.6 would tell us we have 100 ohm resistance at our first load. Going over here to our second load with 10 volts on the drop, and we have 400 milliamps going through there, we can take the 10 and divide it by 0.4, and would tell us we have 25 ohms running through that load, or resistance of that load rather. Now on R3 we have 30 volts, and we have that same 400 milliamps, so we take 30 and divide it by 0.4, and that would give us 75 ohms, for a total of 100 ohms on this branch of resistance. Now over here on R4 we have 40 volts, and we go down here, we have the 200 milliamps, so 40 divided by 200 milliamps would give us 200 ohms. Now we could do the reciprocal formula, the product over sum in this case, and then add the 100 ohm of R1 and get our total resistance, but we don't need to do that. We can use the Ohm's law. So we have 100 volts total, and we have 600 milliamps total, so we can simply divide 100 by 0.6, and that'll give us what I rounded out to two significant digits, 166.67 ohms. So if we can piecemeal one like this, given the right values and everything, and we can do so using the node rule, the circuit rules, Ohm's law, and the power formula, a little bit of metric notation in there, and we're not going to go ahead and work one out all the way through the calculations and redrawing it. We'll do that in part 8. That concludes part 7 of the electrical circuits tutorial series. Thank you.